We now arrive at the cutting. One must distinguish between three aspects of the cut: the displacement speed of the knife, the occlusion duration of the port, and the cutting frequency. One would want a quick displacement of the knife because the speed is going to affect the quality of the cut, which is the principal quality of the handpiece. It is of course general knowledge that a knife with a quicker displacement cuts better than a slower one. The occlusion duration of the port by the knife is also important. In the traditional system, the duration of the port's opening is equal to the duration of its close, no matter what the frequency is. With a system of short occlusion duration, the opening duration would be infinitely greater than the closing one. This allows the operator to greater control the flow, since the port is now opened twice as long compared to the traditional system. Bidet and Collin also tested this difference. At each cycle of a second, the opening duration of the port is 0.45 seconds in the classic system versus 0.9 seconds in the short occlusion duration system. This is why with a Venturi pump in BSS at 60 cuts per minute, you will have an aspiration flow in a classical system that is half the flow obtained with a short occlusion duration system. With a peristaltic pump, the flow will be the same no matter which system is being used. In fact, the pump itself eliminates the same quantity of fluid in 30 seconds in a classical system as it does in 1 minute for a short occlusion duration system. But hydrodynamic consequences will result. As we have already seen, when the port is open, the intraocular pressure is lowered by the aspiration flow, and the pressure at the port is just slightly less. Thus there is a tiny gradient of pressure which yields a tiny aspiration flow that can be completely controlled. When the port is closed, the ocular pressure increases since there is no longer any aspiration. The pump continues to turn, creating an augmentation of the pressure since one is in occlusion. In reopening the port, the higher gradient of pressure will be responsible for a strong, uncontrollable flow before returning to normal. Bidet and Collin demonstrated this well, for with a classic system, the pressure at the moment of closure considerably drops, while the intraocular pressure rises to its rest level, with variations of 25 millimeters of mercury. When considering the short occlusion duration system, outside of small variations due to shock waves caused by the movement of the knife, the pressure difference between the handpiece and the eye is quite stable. The intraocular pressure will only experience variations of 2 millimeters of mercury. The surgical consequences are immense. Even at a low flow level in a traditional system, the gradient of pressure that has time to increase during the closure of the knife is going to bring about such a force at the reopening that the retina will move, and this movement will not be controlled by the operator. With the short occlusion duration system, the gradient of pressure will not have enough time to increase, and the retina will not suffer from movements that we cannot control. For me, the control of cutting frequency is as important as the control of the aspiration flow, for both often vary together. Here is an example of a vitrectomy performed due to perforating injury. At the beginning, for the central vitrectomy, since I had a large aspiration flow, I cut quickly at 600 to 800 cuts per minute, in order to avoid all peripheral traction that could have caused a tractional distant tear to occur. In order to remove the anterior haloid, or, as I'm going to perform now, the posterior haloid, I slowed the cutting frequency and stopped from time to time to allow the structure to enter the port before detaching them. Now it's done. I start again with high-frequency cutting, moving on to the peripheral vitreous. Here also it is a phakic eye, so I will perform a manual indentation. For the peripheral vitrectomy, I will decrease the aspiration flow. I will then also be able to decrease the cutting frequency without risk. Then this hemorrhaging vitreous, located at the vitreous base, that we could not approach directly without damaging the lens, will have the time, between each cut, to be aspirated towards the base. One sees the necessity to simultaneously vary the aspiration flow and the cutting frequency at each moment. We then absolutely need a two-dimensional linear pedal. Let's go back to our patient with a proliferation adherent to the capsule. With a fast cutting frequency, this proliferation will not be taken by the handpiece. In order to remove this proliferation, we will first have to decrease the cutting frequency and slightly increase the aspiration flow. So we will control the two successive actions as if we were working with two hands. The first attracts the structure to the port, and then the second cuts at the desired moment. We will then act as a hairdresser who holds the hair tightly with her comb before cutting it precisely at the desired length, as we do for cutting those two strings close to the suture knot, and as craftsmen have been doing for centuries, each time an adherent fiber must be cut. But if we don't control the first action, the aspiration flow, a low cutting frequency, can induce retinal damage. This is why some operators working with vacuum control have wanted a high-speed vitrectomy. Let's see the results. Here I'm cutting at 600 cuts per minute. The retina moves because the adherent vitreous has the time to come in the port. Now I'm using 1,800 cuts per minute, and a miracle occurs, for the retina no longer moves, giving the operator the illusion of having finished an excellent vitrectomy. But the problem with this illusion is that the procedure is very incomplete. If one passes a needle just above the retina, one is going to pull all the adherent vitreous cortex, which has not been removed during this high-speed vitrectomy. On the contrary, with a low aspiration flow and no cutting, we are able to detach this cortex. High-speed frequency cutting permits a very secure but very incomplete vitrectomy to be carried out, since it only allows one to cut the extremities of the fibers. It's no secret that if we want to remove more adherent vitreous, we must first make it come to the port by a low cutting frequency, and thus must also cause the retina to move. Then, to avoid retinal damage, we must control the aspiration flow. At the end of this presentation, we can see that all is not as simple as we have been led to believe. But just like a good car is one that allows the driver to perfectly control its speed and braking, a good vitrectomy machine will allow the operator to have, under precise control, all the parameters he or she will need, parameters which first obey the laws of physics. The goal of this long and boring video was to recall all these laws of physics for those who, like me, used to sometimes skip their physics class.